Okay, hello everyone and welcome to the Black Hole. So today we have a talk by Dr. Pervez Hoodbhoy. He already gave a talk at 3:30, and today in our audience we have 40 kids from the Burak Space Camp, which is an annual camp held in Islamabad, selecting 40 of the most talented students from all across Pakistan. So we are honored to have you guys here and do participate and ask questions and learn as much as you can. Uh, Before starting, I would ask all of you if you have any mobile phones to please turn them to silent mode so that there is no disturbance during the talk. And when during the question answer session, please wait for the mic to reach you and only then ask the question. So today's topic is quantum entanglement, quantum computers, cryptography, and teleportation. So all about the quantum world and its applications. So you will learn a lot during this talk. So let's welcome Dr. Pervez Hoodbhoy.
Okay, good. So we're going to talk about quantum matters. Quantum mechanics started about 120 years ago, 1900 and something. And it was a branch of physics which became necessary because there were so many contradictions that classical physics was encountering that people were just very puzzled how to resolve them. I'll give you an example. When you take a charge and you accelerate it, it gives off radiation. And so it loses energy. And so after a while, its energy is gone. It's been converted into radiated energy. But on the other hand, if you think about an electron which is going around in an orbit around the proton, around the nucleus, well, it's accelerating, isn't it? Even if its speed is not changing very much, but its direction is, and so that's acceleration. So it should be the case that an atom, the electron of an atom, should be continuously radiating energy, and that means that that atom will collapse. But the fact that you and I have atoms within us and we are still around, that says that there's something very mysterious. Then there were a lot of other things that were noted. One was that if you throw light onto a certain metal, then you can knock out electrons from that. But if you change the wavelength of that light and you decrease its frequency, or you increase its wavelength beyond a certain point, then the electrons stop coming out. And it doesn't matter how much light you throw at it, there's still no electron that is knocked out of the metal, and that was also very puzzling. This gave rise to the idea that light comes in little packets of energy called quanta. Quanta means a little packet of something, in this case, a packet of energy. Okay, so I will not try and tell you how quantum mechanics developed, because that will take us a very long time. But let me show you, let me show the faces of those who had invented quantum mechanics. And here, when the projector comes on, you will see most of the important people of that time. This was a conference that was held in a place called Solvay. And this was, oh, by the way, this is the title of the lecture today. And why have I put cats over there? Because these will be Schrodinger's cats. Okay. All right. Here is Schrodinger. here is Heisenberg, famous for the Heisenberg uncertainty principle. Do you recognize who that is? That's Einstein. No. This is Pauli.
This is Pauli. So Heisenberg का ये गलत लिखा हुआ है ना. Heisenberg should be this. Pauli का ये इस तरफ एरो पॉइंट कर रहे हैं. ये Pauli है.
अच्छा.
एरोस थोड़े.
हाँ, ये इधर होना चाहिए. Yeah. Okay. Yeah. And you know who that is?
Mary Curie.
No. That's Mary Curie. Who's he? He's Planck. Max Planck. Yes. So these are the famous people of those times. This was held in 1927. That's more than 100 years ago. Okay. Now, quantum mechanics is exceedingly successful. In fact, the calculations that we do with it are accurate to the point where, some of the things that we've measured and calculated, they agree to 12 places of decimals. And that's incredible accuracy. So, for example, we can predict that an electron spins around, okay? And because it's charged and it spins around, therefore it's a little magnet. Every little electron is a little magnet. How strong the magnet is, we can calculate, but also measure. And the two agree to such an incredible precision that there's no way that quantum mechanics can be wrong. When I say it can't be wrong, we always leave a little bit of doubt open, because in science we agree that if there's some contradictory evidence, then we will throw that theory away or we'll modify it, but so far nothing. However, even though we, and among those we, myself too, use quantum mechanics just like we use Newton's laws. You use Newton's laws to figure out how far a projectile will go. We use Schrodinger's equation to find what frequency of light an atom will release. Things like that. In spite of all the millions and millions of uses and the fact that your mobile phones and all the electronics that we have today depends crucially upon quantum mechanics. I mean, without quantum mechanics, you would not have the mobile phone, you would not have the computer. In spite of that, there are things that we find ourselves puzzled by. So now let me tell you what is puzzling and what led Schrodinger to talk about the cat, and then how that cat issue becomes one that so engages a person, a physicist, that he is led into a different direction altogether. Okay, so here are two separated protons, but there's only one electron. Okay, so if that electron goes around this proton, which I've called A, then we will call this the state A. In fact, we give it a name. It's called a ket, K-E-T. That's just a name. If that electron goes around the proton B, then this system is in the state B, ket B. All right, so the electron is either on this proton or on that proton, and so you would say that it makes no sense to say that it is both on A and B. Just like it makes no sense to say that a switch, which is normally on or off, to say that it is both on and off doesn't make sense. But quantum mechanics is not about common sense. It's something it's something very weird. Okay, now, suppose I was to try and find out whether that electron is here or there. If I make a measurement when the system is in this state, I will find it either on A or I will find it on B. It can't be on both. In this particular case, I will find, if I make 1,000 observations, half the time, roughly, I will find it in state A, and half the time I will find it in state B. Okay, if it's so many observations that I'm doing, then it makes sense that to say that this over here, the square of this number over here squared is the chance of finding it in state A. This number squared is the chance of finding it in state B. However, note one thing. It's very, very important. As soon as I make an observation, it becomes either A or it becomes B, in spite of the fact that the state was a mixture of the two, equal mixture of the two. Of course, if it's not an equal mixture, then let's say that this number was greater than this number, then I'd find more chance of A as compared to B. Actually, this is an example of what we call a qubit. You've all heard about bits. So bits are, in a computer, there's a switch that is on or which is off. That's one bit. So then you know what a byte is. You know what a byte is? B-Y-T-E? How many bits? 8 bits. Okay. Then we have kilobytes, megabytes, gigabytes, etc., terabytes, etc., etc. Here we are talking of something which is called a quantum bit. Okay. Now this is a quantum system with two possibilities, so 2 degrees of freedom, as we call it. And I gave you that example, but I could have given you, I gave you the example of the proton A and proton B, but I could have given you this example as well. So an electron which is spinning like this, we will call ket 0. An electron which is spinning the other way, we will call ket 1. Or it could be even this. There's a hydrogen atom which in its lowest energy state we can call 0 or we can call A. And if we give it a little kick, if we give the electron a little kick, it goes into an excited state and it becomes another state. And so this would be another system with 2 degrees of freedom. We can make the atom go from one state to the other by shining a laser. So if we take a laser and we shine it onto this, then we can go from state 0 to a mixture of 0 and 1. And if we shine the laser a little bit longer, then we can make it go back to 1. So lots of games that we can play with it. Now, although there are only 2 possibilities, yet you see over here that because this could be any number and this could be any number, therefore, this is not just 2 bits. It's not just 1 bit, it's actually a lot more than that. And we'll come back to this later. Okay, so maybe you were not very impressed by the proton or the electron analogy. Let me give you what Schrodinger gave as to tell us how strange quantum mechanics is. So this is an example that he gave it in a different form. I'll give it in a different form. And I'll ask you to imagine a box which has got a cat and a snake inside. They both wake up at the same time, and then they fight. Either the cat kills the snake or the snake kills the cat. So they wake up and they're fighting inside. After a while, it's decided who's won and who's lost. But you don't know who's won, who's lost until you make an observation, which means you open the box. Once you open the box, you will find either the cat alive or the cat dead. Okay? Now, let's take the cat to be this cat and this cat to be the dead cat. Here, there's half a chance, there's 50% chance that the cat is dead, 50% that it's alive. But you see, when it's in the box, it's in a mixture of these two. Now, how can it be that a cat is both alive and it is dead at the same time? It's mysterious, but yet it's not wrong. See, everything that's mysterious is not wrong. You have to point out a contradiction to say that, oh, this statement is wrong. Suppose there were lots of cats and lots of snakes, so lots of these boxes, then you would have what is called a statistical ensemble. So you make mental copies of all these boxes, and these then, when you make an observation, then you will see that either the cat is alive or it is dead, and that the act of observation then makes it collapse into this or that. Okay, you know, this might sound a little abstract to you, and you'll ask, what was it motivated by? Heisenberg didn't start out from this. Heisenberg started out from the electron. Now, here's an electron. Let's say this is an electron. I want to know where this electron is, and okay, that's easy enough, because the light from that bulb comes, strikes this, goes into my eye. So I know where it is. However, this is pretty heavy. If this was as light as an electron, which means something like 10 to the power minus 28 grams or whatever, then that light which strikes this would cause this to move. So in the effort to see where it is, I have given it a speed, a momentum. And this means that I cannot, and this was Heisenberg's original reasoning, I cannot know where an electron is and also know how fast it is moving. And this gave rise to the Heisenberg uncertainty principle for energy and momentum. So now let me get a little technical. Everything that can be known about us, okay, so first of all, quantum mechanics places limitations on what you can know. As I said, you cannot know, even with the best microscope or the best equipment that there is, where an electron is and how fast it is moving. ये दोनों चीज़ें आप बैक वक्त नहीं मालूम कर सकते. या तो आप ये मालूम कर सकते हैं या वो मालूम कर सकते हैं या ये किसी हद तक मालूम कर सकते हैं और ये किसी हद तक मालूम कर सकते हैं. Whatever you can know about a system, that system could be a cat, that system could be an atom, that system could be a molecule, It could be the Earth, if you think of the Earth as a quantum system, although it gets harder and harder as you have more and more degrees of freedom. Still, all that information is something called the state vector. And that's given this symbol, this ket, this. In quantum mechanics, if you know what that vector is, then you know everything about that system. Okay, so now we had just talked about qubits, that there's one qubit and another, and if you take a mixture of one and the other, then the square of this is the chance that you will find this, square of this is the chance you will find that. And of course, the chance of finding either this or that is 1. Because you've got to find this. If you don't find this, it's got to be the other one. Okay. So that's why the sum of those two numbers is 1. So this is what is called the Born rule, Max Born. And by the way, I think Born can be seen over here. Let me go back. I think this is Born and this is Heisenberg. नहीं पॉली तो बूढ़ा था उस वक्त.
नहीं पॉली सर वो है यंग था. पॉली तो बिल्कुल यंग था उस टाइम. वो पॉली है हाइजेनबर्ग के साथ. और
नहीं Born I think is here as well, or is he this one?
बोहर के साथ.
ये तो नहीं है.
ये बोहर है. बोहर के साथ लेफ्ट पे शायद बॉर्न है मेरे ख्याल से. बोहर के लेफ्ट, बोहर के राइट पे.
तो ये रिसर्च प्रॉब्लम है कि कौन कौन है इसमें. Okay. But he's also there because he was one of the greatest physicists of that time. So that's the Born rule that I was telling you about, that this number squared plus this number squared is 1, and this is that probability, and that is that probability. Now what if you have not just one electron, but you have 3 electrons? Then the state vector will require 3 of these, 1, 2, 3. And you can make various combinations from these. So you can write this psi as this. Now I will come to what is called entanglement, and entanglement is basically the statement that if I have 2 entangled systems, that I cannot write the state vector as being the product of state vector 1 and with the product of state vector 2. You know, this is a little abstract. मगर मसला ये है कि क्वांटम मैकेनिक्स है एब्स्ट्रैक्ट. ये हमारे रोज़मर्रा के तजर्बों में शामिल नहीं है. एक ऐसी अजीब दुनिया है जो क्वांटम मैकेनिक्स डिस्क्राइब करती है कि उसको तसव्वुर करना आसान नहीं है. मिसाल के तौर पर मुझे ये पानी की बोतल इधर दिखाई दे रही है ना, लेकिन अगर मैं एटॉमिक साइज का होता तो हर चीज़ में लर्जिश होती. दिस वुड बी jiggling around like that. I would not know where it is, how fast it is moving. Everything would be indefinite. अब तो मुझे ये पता ना, I know that if I throw a stone, it will go land in a certain place. In the world of quantum mechanics, if I throw a stone at the same speed as I threw earlier, it will land somewhere else. That determination, that definiteness is lost. And so if you were of the size of an atom, let's say the size of an electron, the world would look very, very different to you. We are not used to that, and so all these things are a little bizarre. Okay, now let me tell you what is entanglement. तो यहाँ आपको क्या नजर आ रहा है? What do you see over here? One snake is eating the other. So this white one has eaten this yellow one, but the yellow one is eating the white one. And the snakes are entangled with each other. You cannot separate the two. Mathematically, you cannot separate the state vector into a product of state vectors. You can't write psi is equal to psi1 times psi2. If you could, then they are disentangled. Then entanglement is 0. So something like this, 0, 0 plus 1, 1, cannot be written as something times something. If it could, then it would not be entangled. Okay, and this is a subject that for which this person, John Bell, got the Nobel Prize for, but I won't go too much into the details. But I'll tell you why this has become such a big issue. And the story starts in 1935 when Einstein wrote a paper with these two other people, Podolsky and Rosen. अच्छा देखिए, आपने आइंस्टाइन को उधर बैठे हुए देखा था ना, और श्रोडिंगर भी था, और हाइजेनबर्ग भी, और पॉली भी, और बॉर्न भी, ये सारे लोग थे, अगरचे हम इनको कंफ्यूज कर रहे हैं, लेकिन थे सारे उधर. Einstein was one of the founders of quantum theory. And you know, he got the Nobel Prize for something very minor, the photoelectric effect. His big achievement, which was the theory of relativity, got no prize. But that's another story. But Einstein, even though he was one of the founders of relativity, said, I don't believe it. I don't believe all this chance business. K electron might be here and might be there. It's mathematically it's okay, but it can't really be true, because life, meaning physics, has to be definite. There should be no element of chance. अब देखिए ना, न्यूटन्स लॉज में क्या है? F equals ma. F equals ma से आप क्या निकालते हैं? Everything in the classical world. You see how the planets go around the sun. You're able to predict where Mars will be, Venus will be, not now, but 1,000 years later. And it's perfectly predictive, definite, and deterministic. So he said, real physics ought to be like that. I don't like this idea that sometimes the electron is here and sometimes it's there, and I can't know everything about the electron. I should be able to know everything about the electron. I mean, electron meaning all particles, not just electron. And he said, very famously he said, God does not play dice with the universe. So God is not a gambler who throws dice. He has to know everything. God made everything, so damn it, he should know where every electron is, where every proton is, and how fast they are moving. And if he doesn't know, then we are wrong. So Einstein was a very clever fellow. He invented, together with these two other people, this paradox, which I'll explain to you. So here is a particle. This particle doesn't spin. And it's, well, if you just let it be there, it'll stay there, it won't move from its position. Then this particle breaks up. Now there are two ways that it can break up. and it breaks up into particles, one of which spins this way, one of which spins the opposite way. So the two spins cancel each other. But even though I've drawn this spinning this way, it could be spinning this way. And this one then would have to spin the other way. अब इसका भी चांस है, उसका भी चांस है, मगर बात फिर चांस की आ गई. Okay, now suppose this particle travels far, far away. Suppose it travels to the other end of the galaxy. And there is somebody at that end of the galaxy who catches the particle and says, aha, it is spinning this way. Now, if it is spinning this way, instantly, without any time lost, the other particle will start spinning the other way. अब जरा सोचिए, इधर ये किया और इसका स्पिन देखा, तो उसका असर उधर जाके पहुंचा. Millions of light years away, but instantly. Is this allowed? Does it make sense? Why? Because an effect cannot be transmitted faster than the speed of light. It should take you millions of years. It should take millions of years for it to be known that I have found the electron spin to be this way. But instead, according to quantum mechanics, that has instantly changed its direction of rotation. So this became known as the Einstein-Rosen-Podolsky paradox, because it seems to show that information is traveling faster than the speed of light. Achha, making a measurement on one fixes the other. अच्छा शायद आप okay, so instantaneous communication is something that is ruled out, and so quantum mechanics seems to be wrong. Maybe you're not very impressed. Maybe you're not very impressed. तो मैं फिर बिल्लियों की बात दोबारा शुरू करता हूँ आपसे. तो इस डब्बे में 2 बिल्लियाँ हैं और 2 सांप हैं, और ये t=0 पर जाग जाते हैं और फिर इनकी लड़ाई होती है, और एक बिल्ली मर जाती है, एक जिंदा रह जाती है. मगर कौन सी बिल्ली जिंदा है और कौन सी मुर्दा है, मर चुकी? अब ये हो सकता है कि ये बराबर ना हो. Don't worry about the fact that I've chosen this and this to be equal. If they are not equal, it means the probabilities are different. But this is the state. And now what I'm going to do, अब जरा ये देखिए, एक बिल्ली को मैंने उधर भेज दिया, एक को इधर भेज दिया. इस डब्बे को जो ही मैंने खोला और देखा कि इसमें जिंदा बिल्ली है, तो दूसरी वाली मर जाएगी. मरी हुई नहीं थी, मर जाएगी. अगर मैं खोलता हूं और ये देखता हूं कि ये मुर्दा है, तो वो जिंदा हो जाएगी. Bizarre, isn't it? My opening a box here will cause a cat over there to die or to come alive. अगर मुर्दा है तो जिंदा हो जाएगी, अगर जिंदा है तो मर जाएगी. So this is okay. Now let's come back to qubits, because I hope you're impressed by this. Okay, so suppose I have a state like this, which is an equal mixture of this and this. If I make a measurement like open the box or somehow interact with these spins, then there's 50% chance that I will find it in the state 1, in the state 0 or in the state 1. लेकिन एक दफ़ा ये उसमें पहुंच जाए तो दोबारा इसको देखने से कोई फ़र्क नहीं पड़ेगा. Then 0 will remain 0, 1 will remain 1. Now I want to come to the topic, which is quantum computers. And quantum computers work entirely on entanglement. देख कितनी अजीब बात मैं कर रहा हूँ ना, कि कहीं बिलियों की बात कर रहा हूँ, कहीं स्पिन्स की बात कर रहा हूँ, कहीं atoms. It seems so bizarre, but here is actually a quantum computer that's in the process of being made. I don't know, it is she. So this person is, this person is making a quantum computer, and this is at MIT. Now, it's not the kind of quantum computer. It's not the kind of computer that is like this. This is a classical computer. जो आपका लैपटॉप है, that's a classical computer. अच्छा, the thing is that it's got qubits inside, and these qubits should not be disturbed, otherwise they will give false information. So to prevent false information, it has to be cooled down. So this is a refrigerator. All this is refrigerated, but you know, it's not like your house refrigerator. This cools it down to 0.01 degrees Kelvin. यानी कि एब्सोल्यूट जीरो से थोड़ा सा ज़्यादा. You can't get exactly to 0, but you can get close to 0. Now, this tells you that quantum computers are not going to take over your regular computers anytime soon, but who knows how in the future qubits can be designed so that you don't have to cool them down so much. तो चलिए अब मैं आपको इसमें ख़राबी क्या. My computer बड़ा बेहतरीन लेनोवो है, 2 लाख रुपए का मैंने ख़रीदा. ख़राबी क्या है इसकी? It's sequential, which means that it handles bits one at a time, and it handles problems one at a time. That's one problem. And that means if I have a very, very big problem, then it's going to take a very, very long time to go through, because each bit has to be processed, and processing that bit takes time. So the more bits a program involves, the greater the amount of time. The other thing is that this classical computer has got transistors inside. Now everyone knows what transistors are, right? What do transistors do? You make logic gates out of computers, and what that means is if you put a voltage on the gate, then it will allow current to go through. If you remove that, then it will not, or something like that. So here is a transistor. There's a source of electrons. Here's where the electrons are collected, and here's the gate. By changing the voltage at the gate, you use it as a logic device. Now the problem is that in going from the source to the drain, the electrons have to pass through the material, and if they pass through the material, they get knocked around. If they get knocked around, that means they lose energy, which means that you have to supply the energy so that the electrons can keep moving, which means that your computer gets hot. Now, your computer doesn't get very hot. I mean, it does. On a hot day, you can really feel your computer getting hot, right? The problem is that if you make chips smaller and smaller, then they have to then dissipate all that heat. And there's only so many transistors that you can put. And ultimately what happens is that your computer will destroy itself because of heat. In your daily life, where does heat occur? Friction. If you rub your hands, you put soap on them, they don't get hot. But if it's rough, you get heat. So wherever there is friction, there is dissipation. Okay, now what is the thing? हैं? कोई सवाल था? नहीं. Okay. Now, friction is something that makes a process irreversible. When I do this, what have I done? I've created heat. That heat has dissipated. It's maybe some has gone into this hand, some into that hand, some into noise, some into whatever, heating up the air. If you try and go back in time, you will not recover that energy. That energy has been lost. So basically, we want to now stop the wastage of energy. Because if you waste energy, then you create heat. If you create heat, you burn up your electronics. Let me tell you why classical computers are non-reversible and they are dissipated. Let me give you another example before this. Suppose I throw a ball and there is no air resistance, then the ball will go up and it will come down somewhere. Okay. If there is air resistance, it will go up and it'll travel a smaller distance, which means that if you make a video of the two situations, you can tell that one is with dissipation and one is without dissipation. You can tell the two apart from each other. Okay, now I'll try and persuade you that classical computers are non-reversible and that therefore they are dissipative, they waste energy. Everyone knows what an AND gate is? Okay. So in an AND gate, if this is 0 and this is 1, if this is 0 and this is 0, you get like over here. If this is 0 and 1, I get 0. If this is 1, 0, 0, 1, 1, I get 1. Now look over here. If I know the output is 0, can I know what the input was? No. You can go forward, but you can't go backwards. So this is not reversible, which means it is dissipative, which means that energy is lost. I said information is being destroyed, but if you destroy information, you also destroy energy. On the other hand, quantum mechanics is reversible. Now I will go fast on this because I don't expect you to know this. But this says that if I have a state vector at an early time, I can know what is the state vector at a later time, and I can get from the earlier to the later, or from the later to the earlier. So quantum mechanics is reversible, but the classical computer is not. Okay. Now let me tell you a little bit about the quantum computer. So this computer of mine, it has many registers inside. In the registers are stored various numbers. So for example, if you want to add the number 7 to the number 49, in one register it will store 7, in the other it will store 49. And those registers can be then brought together for the data, for the processing. In the same sense, a quantum memory is made up of a set of qubits. You all remember what a qubit is. A qubit is a piece of quantum information. It has 2 degrees of freedom, but it can be in a mixture, alpha times the first plus beta times the second. So if you have a 2-bit quantum register, it can look like this: up, 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 down, down, up, down, down, with different coefficients. Can anyone tell me what would be the condition on the coefficients?
Square of them equal 1. Addition of
Correct. Anybody agree with that? The square of this plus the square of this plus the square of this plus the square of this equals 1. You have to find either that or that or that. Okay. Now, I'll tell you about a very peculiar thing. You all have USBs. The USB you can plug into your computer, and you can copy a video, or you can copy a song, or you can copy a PDF file or a Word file or whatever. They're all zeros and ones, you know that. And then you can give it to your friend who can then make more copies. So making copies is something that you can do with classical registers. But with a quantum register, as soon as you try to make a measurement, that register collapses into either this, or this, or this, or this. And so the act of measurement destroys the register. So it's, you see, is going to be very different from a classical computer. I don't expect you to understand this, but I have to tell you this anyway. You see, in my lecture earlier, I was telling you in just words. बात ये कि quantum mechanics is all about mathematics. तो ये जो बात है ना, मैं ज़बानी तो बता दूंगा, लेकिन अगर इसको गहराई में समझना है तो इसकी मैथमेटिक्स समझना होगी. मगर मैं ज़बानी बताता हूँ है क्या. Suppose that you have a state and you want to make a copy of that state, a clone of that state. Quantum mechanics says you can't do that. So I can't clone a register. I can't clone any system which is made up of qubits. Now you also are made up of qubits, aren't you? You are governed by quantum mechanics. और तो कोई चीज़ नहीं है ना. Now quantum mechanics says I can't clone you, which means I cannot make an exact copy of the state that you are in. That says that there are only some things you can do and other things that you cannot. So now let me tell you further differences. How does a classical computer work? You suppose you want to add two numbers together. So you bring that number, and so fetch, execute. Then you go on to the next number, next task, fetch, execute. Quantum computers don't work on that principle. They work on something that I'll just explain. What they work on is you first prepare the state, then you let it evolve in time, and then you make a measurement. Once you make the measurement, you've destroyed it. In fact, so prepare, evolve, measure. Prepare, evolve, measure. No longer fetch, execute. So now here I'm going to tell you the real advantage. Instead of the computer bringing the bits in one at a time, the data in one at a time, what the quantum computer does is it works on all the information simultaneously. So instead of 1,000,000 problems done one at a time, it does one single computation. And so for that reason, because it is doing this parallel work, it is in principle much faster. I'll tell you exactly how much faster. But this is what a quantum computer looks like. So you prepare, evolve, measure. How much faster is a quantum computer? I'll just hint at this. There is already a quantum computer that Google has made, which is able to solve a problem in a few minutes, that all the supercomputers in the world, if they were made to work on that problem, would require many years. And that's now. You can imagine what's going to happen by the time you become quantum computer mechanics, or whatever profession you take. Doing something in minutes that would take a supercomputer years, you can see how much more powerful they're going to get in the future. But you shouldn't think that these computers, the classical computers, are going to go away, because the quantum computers don't know how to solve all kinds of problems, whereas this one does, because it has the software. And writing the software for quantum computers is probably the most difficult thing, more difficult than the hardware. That's all I'm going to say about quantum computers. And one last thing that I have to tell you is about quantum teleportation. So, what is quantum teleportation? It's about taking a quantum state here and moving it here. Maybe a mile away, maybe 1 centimeter away, maybe on the other side of the galaxy. We're just saying that that's what teleportation means. So why shouldn't I simply make a copy of whatever state there is and send it over by TCS? What's wrong with that? Is it possible? Yeah.
It takes too long. It takes longer than it could.
But it's possible.
No. Yeah.
Quantum physics I'm not sure, but I think quantum physics follows the no cloning theorem, so it can't be cloned.
Good, good, good. That's the answer. You can't make a clone. You can't copy the system. So now here is a very peculiar situation. I can't make a copy, but through teleportation, I can take this quantum state and transfer it there. How on earth can you do this? देखिए ना, बड़ी अजीब बात है कि अगर मुझे इसको उधर तक पहुंचाना है तो पहले तो मुझे ये देखने की जरूरत है कि इसके अंदर है क्या. I can't do that. The no cloning theorem stops me. So the way this is in the literature, this is described is Alice has a certain quantum state, let's call that A, and Alice wants to send teleport that state to her friend B, Bob. Okay, now this requires some pretty fancy thinking. Because of the no cloning theorem, you can't make a copy. But what can be done is from a third source, send a photon, send a signal here to Alice and a signal to Bob, and then a bunch of complicated things happen, which I'm not going to explain, but just tell you in some rough detail. So Alice wants to teleport particle 1 to Bob. That's the problem. What that means is that particle 1 is in this state. Alpha and beta are any numbers whose squares add up to 1. Okay? So now two particles, this and this, one is sent to Alice, one is sent to Bob. And then this stuff I can't explain because it will take too much time and we'll need to do some more. I'll need to tell you more. Alice now takes the particle which is sent to her and she entangles it with her own particle. And then she makes a measurement on that, and then she telephones Bob that this is what I found. You see, the thing is that, so why could she not have अपना स्मार्टफोन उठाकर वो बॉब से कह देती, hey Bob, here is my state. Why could she not have done that? Yes, yes, yes. You see, Alice doesn't know the state that she is sending to Bob. If she makes an observation on the particle that she has, it will cause that state to collapse. It will become either 0 or it will become 1. So she has to send information that she herself doesn't know. उसे खुद पता नहीं कि वो क्या information बॉब को भेज रही है, लेकिन वो यूं कर सकती है कि एक जो न्यूट्रल सोर्स है उधर से एक पार्टिकल लेकर अपने पार्टिकल के साथ एंटेंगल करे और दूसरा पार्टिकल जो बॉब के पास गया है, बॉब उधर इंतज़ार कर रहा, जब एलिस अपना मेजरमेंट कर लेगी तो फिर वो बॉब को फ़ोन करके बताएगी, कहेगी कि I found state 0 or I found 1, and then Bob will make the appropriate adjustments at his end. So let me show you the last slide. One after this. So basically the particle 1 is disassembled and combined with the entangled pair. Alice measures the particles 1 and 2, and then she produces these outcomes, and then she picks up her phone, and so it goes like this. तो न्यूट्रल सोर्स से ये दो पार्टिकल्स भेजे जाते हैं. This one goes to Alice, this one goes to Bob. Okay. अब इनकी आपस में गुफ्तगू हो रही है. In a quantum, but Bob, in a quantum world, how can we be sure? How can I know that you love me? Yes or no? He says, oh, you are the one for me. And then, okay, so that's the state, alpha 0 plus beta 1. She makes those measurements. Then she sends the phone. She's making those measurements. This shows the measurements that she's making on her qubits. And if she finds that, then she's communicated alpha 1 plus beta 0 to Bob. If it's so, in the end, it's a little complicated. I don't want to get into the protocol. But what has happened is that Alice has succeeded in sending her quantum state to Bob without making a measurement on her quantum state. And now I have to tell you that this is an experiment that has already been done. So this was, I think, 1 year ago, more than that maybe. A quantum state has been transmitted, has been teleported from here to another place which is some miles away, going through a satellite, and this is a Chinese group which has done it. So the Chinese are, everybody actually, Chinese, Americans, whatever, they are all working very hard on teleportation. Now in science fiction, you read about Star Wars mein hai, there's somebody standing over here and so lasers shine on him. They get the quantum information, and then that person is destroyed, and his image is created elsewhere. He is teleported elsewhere. So he can, this way, go from one end of the one end of the solar system to the other end just by teleportation, and this happens at the speed of light. Not faster than the speed of light, but at the speed of light. Why? Why?
Because quantas are light that are packages of energy. Therefore, they are
So
light.
over there we had a comment that the reason is that information cannot travel faster than the speed of light. Is that what you said? Okay. But where did that exactly come about?
Einstein said that.
No. Between Alice and Bob. See, Alice has to pick up her phone and say, I made a measurement and this is what I found. Thereafter, Bob can look at the particle that was sent to him, which is entangled with the particle over there, and looking at that particle, he is able to figure out what the state that, he is able to figure out the state that Alice had sent him. But he needs that phone call from Alice. And Phone calls can only travel as fast as the speed of light. So now this also tells you about the two Schrodinger cats. जैसे ही मैं इधर ये डब्बा खोलता हूँ और देखता हूँ कि बिल्ली जिंदा है तो दूसरी मर जाती है लेकिन मुझे उसकी खबर नहीं होगी. वो कोई उधर से मुझे फ़ोन करके बताएगा कि वो बिल्ली मर गई. But that phone call can travel at the speed of light only, not faster. Look, this is not so simple to understand, and Einstein really puzzled everyone with his paradox. But thinking about this has led us to the idea of entangled states and to the idea of quantum computers. And today, as I said, the proof is in the pudding. Now you have quantum computers which are faster than classical computers, and they're going to get faster and faster. So the moral is, the ending point today is, the world is complicated. Abstraction should never be underestimated. अब देखिए कितनी अजीब बात है, हम बिल्लियों की बात कर रहे हैं और कहीं कंप्यूटर्स की बात कर रहे हैं और कभी इलेक्ट्रॉनिक्स की कर रहे हैं, कि क्या ऐसे लगता है कि किसी का दिमाग उड़ गया. But those great ideas came from such things. Okay, done. Let's have questions now. Priority is to the students, but you can ask. Yes.
Assalamu alaikum, sir. Sir, thank you so much for your talk. So according to the second law of thermodynamics, we know that entropy of the universe will increase and energy will ultimately go towards degradation. We cannot recover it. But you have mentioned the quantum computers are reversible. I want to understand more about that. How doesn't it break second law of thermodynamics? Or am I understanding it wrongly?
You are understanding it correctly. All I want is chalk. Second law of thermodynamics says that delta S, which is delta Q over T, this is always greater than or equal to 0 for an isolated system. And if it's an isolated system, well, that means delta Q is 0, so delta S will always be increasing, or non-decreasing, I should say. Acha, so in a quantum computer, because there is no dissipation, delta Q is 0. वो इसीलिए मैंने बात की थी ना कि गेट्स को रिवर्सिबल करने के लिए आपको ऐसे गेट्स बनाने हैं जिसमें कोई डिसिपेशन ना हो. तो उस सूरत में उन गेट्स को रिवर्सिबल होना चाहिए, और उसके माने फिर ये बनते हैं कि जितने इनपुट्स हैं उतने आउटपुट्स हैं. Those gates in which the number of inputs is equal to the number of outputs, those are non-dissipative, और फिर एंट्रोपी नहीं बढ़ेगी. Okay.
I just wanted to ask that since there are many advancements that are coming in science recently, this might seem a little irrelevant, but at the same time I was really curious about this. I just wanted to ask that as there are more and more advancements, how do you think it's going to shape global politics as certain countries have more developments in concepts like quantum physics and quantum teleportation, as you mentioned that China is already conducting these experiments?
You can look at past history and know that those countries which master technology earlier on are the ones which will have greater GNP, they will have greater say in world politics, they will be perhaps more aggressive as well. Sad to say, but look, the fact is the most advanced technology, scientifically advanced country is Israel. And you can see what it's doing in Gaza. And there's a lesson to be learned from that if the Arabs, if the Palestinians, if other peoples saw the source of power as lying in science, then they would have lifted themselves up and avoided the catastrophe that we are seeing today.
Thank you.
So I have two questions. The first one being that you explained how energy can be recovered in quantum mechanics and quantum entanglement. Can you explain more on how that happens? And the second thing being, I forgot the second thing. Could you just explain this?
Energy is not directly related to entanglement. So I'm not quite sure what you mean. Maybe you mean something else. Try and rephrase your question.
I mean, how does that specifically work, where if energy is still lost, it can be recovered? Because we see how energy is lost through light, heat, whatever. And then you said in quantum mechanics, heat is lost in these quantum computers. So how is that recovered in that sense?
Heat is, okay. So let me try and say this again. In a normal computer, you have this kind of gate. So it doesn't have to be an AND gate, but it could be something else, okay? NAND gate, for example. You have one output, but you have two inputs. Knowing this, you cannot go back. And so this is non-reversible. If it's non-reversible, that means like friction, energy is being lost. This is dissipative. In a quantum computer, you will have this situation. The gate will look like this. Two inputs and two outputs. And it's this is one of these will be what is called the control line. The other one will be the data line. So the thing that I was trying to emphasize was that reversibility means that you don't lose energy. Irreversibility means that you do lose energy. If you lose energy, then you increase entropy.
I remember my second question. So the second question was, you told how information is being passed at the speed of light, and like you said, like some miles it would travel like within milliseconds, or it traveled at the speed of light. So do you believe that in the future we can transport large amounts of matter, like people, through that speed of light and teleportation, like you said, or we could just send information, other irrelevant of matter and all that?
At the present time, it is possible to send one qubit from here to here, teleport. And it's through that procedure, the Bob Alice one, where you have a third source. One particle comes here, entangles here, the other goes there, entangles there. And then there's the classical communication channel in between, okay? That's for a single qubit. I think there are, see, I'm not an expert in this field. But I think that 2 qubits have also recently been teleported. Now, 2 qubits is a lot more difficult than a single qubit. When we talk about something that is made up of a million or a billion qubits, then the difficulty is something that I think will be overcome maybe 1,000 years later or whatever. But in principle, so you see, in teleportation, let me emphasize this point. in principle, if I want to teleport you to the other side of the galaxy, the flesh and bones that you are made of will not be transported there. They will be created anew. असर नौ नए सिरे से वो तमाम टिश्यूज वहाँ पर बनेंगे, like from a 3D printer. 3D printer का पता है ना? You give an information and the material is there, and so it joins up everything and will give you the replica over there. Except the difference is that living things are much more complicated than structures that you need for various mechanical applications.
So then what will happen to the person who will be available here?
Dead.
Dead.
Not dead, gone.
I have one question.
Because, wait. How? Because to know the state of that person, you will have to destroy him. Otherwise, you will not be able to find out the state of that. Otherwise, you won't be able to reconstruct him over there. See, the point is, I can't make a copy of you, but I can create you elsewhere without your hair or your body tissue going across. Not even one atom from you will go across over there. Information about that atom will go over there, and then it will be reconstructed. A similar atom will then be put in a similar state. Yeah.
I have one question that you give the example of two cardboards or two boards which have two cats inside them. And if you open the one in which the cat is alive, in the other one the cat would be dead.
Will die.
Will die.
Yes.
If you open both of them at the same time, what will happen?
Well, how would you do that? They are... See, I am here and somebody else is over there. Okay, how will I know when to open the box? I'll have to send a signal. That signal will take 5 days or it'll take 5 million years, whatever, depending on the distance. So how will we agree that if I say I'm going to do it now, all right, maybe we can do the following. All right, I think I understand. So I'll phone my friend and I'll say that 1 hour after you get I know the distance. 1 hour after you get my message, you open your box and I will open my box. So then we will open at the same time. Whatever will happen will happen. He will find what he finds, I will find what I find. But I will not be able to affect what he has. I will not know what he has found until he phones me. And that will take 5 days or 5 years or 5 million years.
The whole Alice and Bob thing that you explained, could you explain it once more why Alice wouldn't be able to measure her own dimensions by herself again, and why if she would, it would just destroy her?
Okay. So when I have a state like this, this is a state that is a mixture of A and B. When I make a measurement, this So measurement makes it collapse into A or B. And thereafter, this state has lost the information. So Alice cannot find out what alpha and beta are. All she can say is that there are these two possibilities, A and B.
So she just knows the possibility, she doesn't.
So?
She just knows the possibility, she doesn't know
She
for
doesn't
sure.
know the possibilities. She doesn't know the possibilities. She doesn't know the state. All she knows is if she makes a measurement, she'll find the cat dead or the cat alive. And she doesn't know anything more than that. But still, without knowing, she can transport that state to Bob.
Okay, I'm going to start off with, I have two questions. I'm going to start off with that never is a very strong word, so we cannot be sure, but does that mean that everything in classical mechanics is not fixed?
Everything in classical mechanics is fixed.
It is.
Yeah, because let's take this for example. I take a stone, I throw it, it goes up and then it comes down. I do it today, I do it tomorrow, I do it 5 days later. It always behaves in the same way. So it's two things determine it. One is how fast I throw it, and secondly, the direction in which I throw it. If I do it the same, assuming there's no air resistance, there's no wind or whatever, then this will always, always, always land at the same point, but not if the world is quantum mechanical. Sometimes it'll land here, sometimes here, sometimes here, sometimes here. Different chances.
Okay, is quantum mechanics basically for two objects, two things? And if it is, there could be a trend, because I don't know if you're if you know about the game Eeny Meeny, but Eeny Meeny Miny Mo, there's like a certain trend to that. If you're doing it between two people, it always lands on one person depending on who you started off with. So is it between two people?
No, 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 no. I'm sorry I gave you the impression that quantum mechanics deals with A and B only. Okay. No. Quantum mechanics can describe an atom which has got 90 protons and 90 electrons in it. It can describe the DNA molecule which has got billions of atoms in it. Quantum mechanics describes everything. In fact, it describes the whole universe as well. So certainly it's not got to do with 2 degrees of freedom. It can deal with an infinite number of degrees of freedom.
Okay, lastly, the example you gave, 1 over under root 2. When you cancel out the under root, you get 2 values actually. So does that mean you have more?
What I meant was this, okay. So if it's...
And is this fixed for everything, this certain value?
Again, I apologize for having used this too many times. Yeah. What's the square of this?
It's basically it's just going to be
Nini, iska, if you multiply it by itself, what do you get?
You basically get 1 over 2.
Yeah, and of course 1 over 2 over here. Suppose I had instead if I square this, what do I get? And this?
1 by 4, okay. Yeah.
3 by 4 plus 1 by 4 is equal to 1. So the square of this plus the square of this is 1. In this, for this state, there is a 75% probability that the state A will be found and 25% probability that the state B will be found.
Only positive values.
probabilities are always positive, yes.
Okay.
Yeah.
Thank you.
So you can't talk of a negative chance. Chance always has to be positive, yeah.
In the beginning, you said that without quantum mechanics, we wouldn't have computers and phones. Could you give us some more examples of inventions and things that are relatives to our lives right now that are possible because of quantum mechanics?
Okay. Does anyone have a tumor over here? No? Nothing? No brain tumor, no? Okay, all right. Well, you could, if you had one and you were willing to pay for it, you could go to a hospital over here and ask for positron, electron, tomography, scan. Scan is usually. What is this? Positron, electron. So a positron, as you know, is an anti-electron. The electron and positron, when they meet, they annihilate. They give you 2 photons. And now, literally, here's what happens when you go for your tumor checkup. They give you some kind of a thing to drink. And what they give you is something that gets concentrated in whichever part of your body has the tumor. Once it gets there, then it starts decaying. Well, it's decaying all the time, but when it decays over there, out comes a positron. It finds an electron just next to it, and then out come 2 gamma rays. So you lie down like this after drinking, and you're put in a machine which, so you're lying like this in here, and all around this are detectors. Now, when a photon from here and a photon from here reach, this is the place where you have your tumor. And they can make entire images of what's inside your body. And this is pure quantum mechanics. It's pure quantum mechanics together with Einstein's theory of relativity. Because Einstein said, see, this is incredible. Einstein said the energy is no longer is it half mv squared of a particle, it's this. If you take the square root of this, you get 2 signs. And this second sign was so puzzling to people who were trying to join quantum mechanics to relativity that it actually led to the prediction of antiparticles. And now you're enjoying your tumor scan because of that. Much.
Okay, so when you gave that example of 2 boxes and one of the cats is dead, and when you, let's say, you check one box and if the cat's alive, immediately the cat in the other box dies. Is it the case that the cat actually dies at that moment, or is it that you're just developing a system where you just keep everything up in the air? It's like a model where everything is it's just probabilities, and instead of confirming anything, you just work in possibilities, and so that model is just a powerful model, and when you work through that model, you can work faster and get things done. Is that the case, or is it that actually checking kill does something in the other case?
Fact. I open this, I have killed that cat. I open this, and I have made a dead cat come alive. It's bizarre, but it's true.
Couldn't you say that you've opened the box, and you've discovered that the cat is alive? Hence, the other must be dead.
Not hence.
Because
no.
Because one
No.
dead, there's a live
No,
cat and a
I
dead cat.
I didn't know when I was opening the box whether it would be dead or alive.
You didn't know.
But if alive, that dead. If dead, that alive. Interpret it as you like.
Okay. All right.
Sir, you said quantum computers have to be cooled down to a temperature of 0.001 Kelvin.
Yeah.
So is it practically possible?
Yeah.
So,
But extremely, extremely expensive. So you need a lot of cryogenics for that. But let me tell you why it's necessary. Because if you have an electron that's spinning around, it's a little magnet. Magnets are affected by magnetic fields, and magnetic fields are everywhere. So, for example, you shook your head, that, because you have conducting material in your head, shaking your head meant that you sent some magnetic field towards me. And so the little magnet, the little electron was disturbed by that. This is called decoherence. So to prevent decoherence from destroying the qubit, you have to keep it very, very, very cold. And a lot of effort is how to make qubits less sensitive to noise. You know, in 100 years, you will not have these cryogenics, you won't have these refrigerators with the quantum computers. I think they will discover something else.
so why can't we go from 0.001 Kelvin to 0 Kelvin?
Oh, the third law of thermodynamics says so. You cannot go to zero temperature. That's what the law says. You don't have to believe all laws, but this is pretty solid.
I have like a similar question to the person who asked a question before. The cat in a box, right? So is it like fixed? If like one cat dies, the other has to be alive? And also, is it only like with two boxes, or can it also be more?
See, I invented that two-box thing to make it a little more, mirch masala, but it was actually just the EPR paradox, Einstein-Podolsky-Rosen paradox. He used particles. Here you can use cats. If you ask, can you have more than 3 particles that are entangled? Sure. In fact, in a quantum computer, you would need to have all the qubits entangled with each other. And that's another problem, because the disentanglement or the decoherence is even more important over there. Suppose you have 2 spins which are entangled with each other. It's relatively easy to keep them separate from each other and to prevent them from losing coherence. But if you have 30, it's much, much more difficult. And if you have 300, who knows?
Okay, but like if you explain that in like the cat in a box term, so if you have like 3 boxes, how do you determine which cat is dead and then which cat is alive?
Okay, so if you have 3 cats in 3 boxes and you take them to 3 different places, it's a little more complicated. We'll have to write down the state and see what the possibilities are. But of course, you can have any number of qubits. A qubit is a cat.
Hello, sir. This mind-boggling concept of quantum entanglement, doesn't it make us question everything that we understand about classical physics? For example, gravitational waves and light takes 8 minutes to reach Earth, and we know that nothing travels faster than the speed of light. So anything seems bizarre until it's understood. So maybe if the information in the form of quantum entanglement is traveling faster than the speed of light, so there might be a missing link that we are currently not understanding, because this makes us question our current understanding of physics, the one-dimensional nature of time, the nature of reality, everything. And maybe if quantum entanglement works at a massive scale, maybe events at a planet far away in some other universe that's similar to Earth, the events at our planet are getting influenced by events at that planet. Maybe if it operates at such a massive scale, so it's just mind-boggling.
Okay. हाँ, दो तीन और सवाल. हाँ, अच्छा. You know what you say is very important because it's so dangerous. Because when you hear about quantum coherence and you say, my mind is blown, and then you say, oh, then it could be that something that's happening on a distant planet is influencing me, then you open the doors to astrology, to palmistry, to all kinds of nonsense, to parapsychology, to वो क्या कहते हैं इधर सोचते हैं तो उधर ESP, that's all BS, okay? There is no way that a state over there and a state over here can remain entangled for even a microsecond, even a nanosecond, even a petasecond. So physics guides you through stages carefully. If Einstein had not lived and Schrodinger and all these people had not lived, we would still have been able to predict that the moon will rise on कि ईद कब होगी, कब नहीं होगी, through just plain classical mechanics. It's when we go to other limits, when we talk about electrons, when we talk about particles moving close to the speed of light, then we have to be more careful. But all this belief in ESP, etc., no.
Sir, I have 4 questions if you allow it.
No. 4 nahi wo Shahryar is otherwise going to be very upset.
Okay, I would like to ask, when you said that two particles can be entangled, let's suppose that each particle is one of 3 possible states. If both of them are entangled, if you know one state, you cannot know the other because there are 2 other possibilities. So they're not really entangled.
Okay, so if you have a state, if you have not a qubit but a tribit, let's call it a tribit, 3 states, 0, 1, 2. So I have psi, which is alpha, plus gamma 2. 3 possible states, this and that. And then a second state which also looks like this and which is entangled with it. That makes, when they're entangled with each other, then we'll have to figure out what entanglement and disentanglement means. But that's an interesting separate question that we can discuss separately.
Okay, and lastly, when you said that when we measure a particle or a qubit, that particle or qubit is destroyed. So why is it that when we measure ourselves, our length in meters, we don't destroy ourselves?
Because you're too big.
No, but how does that help? Entropy is still more.
Oh, because you're very classical. You're not. I mean, you have you have so many different states possible to you, available to you, that measurement doesn't affect it. Let me put it this way. Okay, let me give you another. If you have a cricket ball, is that cricket? Can I determine the position and speed of that cricket ball? Yes. Yeah. Why? Because the photon that comes and hits the cricket ball doesn't disturb it very much. So the cricket ball is big, too big to be disturbed by the photon. You are too big to be disturbed by the photon also. In that sense, I was saying. Okay, so we are done now. You can look at the moon. Thank you.
Thank you for taking all the time.
Thank you.